Good morning, and welcome to Rosenblatt's fourth annual Age of AI Scaling Conference. My name is Kevin Cassidy. I'm one of the semiconductor analysts at Rosenblatt, and today it's my privilege to introduce Dr. Scott Hanson to you. Scott is the founder and chief technical officer of Ambiq. Scott is an expert in ultra-low energy circuits. He has a PhD in electrical engineering from University of Michigan, go blue. Also joining us will be Ambiq's IR and head of branding, Charlene Wan. We see Ambiq's sub-threshold technology as a major differentiator in the edge AI applications. And I'll ask Scott to frame our discussion with a few short slides of overview for Ambiq. And then we'll follow up with questions, and I'll open up to questions from the audience. Also, I will add, Scott, I did give myself a Father's Day gift. This is the Ambiq-based Voice Caddy T11 Pro. Works great. Got to use it over the weekend. I saw this as a product in one of Charlene's newsletters, and I couldn't resist buying one. So it's
awesome. Well, first of all, we appreciate that. Thank you.
Great product. Yeah. The floor is yours, Scott.
Perfect. Well, hey, I appreciate you having me here today. Really excited to be here to talk about what is an important topic for us. So I know AI is the focus of this conference, and it's something that Ambiq is thinking about every day. And what I want to talk about briefly here in my opening remarks is how we are specifically solving the edge AI power problem or energy problem. And look, if anybody's, they're reading the news or they're attending talks at this conference, surely what you're seeing is a big discussion about AI, and in particular about cloud-based AI. So the things that the large language models in the cloud, ChatGPT, Gemini, Llama, et cetera, what they're capable of is astounding. We're seeing it disrupt search. We're seeing it disrupt the way code is being written. So the engineers here at our office are using large language models to assist their coding practices. We saw Apple announce summarization features yesterday, and that's something that certainly all the other companies before them had already announced. It's amazing what is being accomplished. But I think the story that's quite a bit less covered, but which has the potential to be far bigger, is how AI is impacting the edge. And we're starting to see it happen, but you're probably not aware of it. It's not something that when you wake up in the morning, it's hitting you in the face in the way that the cloud-based AI is. And so if you're wearing a smartwatch today, which you are, Kevin, thank you, you're more than likely than not, it's using AI to assess your heart health, to assess your sleeping patterns, to maybe do fall detection. But we're also seeing if you're wearing Bluetooth headsets like I am right now, more likely than not, it's using AI. It's going to be using neural networks to clean up speech, to do speech enhancement. One of the interesting ones is the Bluetooth link that connects the headphone to my phone is most likely using neural networks for error correction, to detect for drop packets and correct for those. But there's all sorts of other use cases. Machines are using neural networks to detect their health. So the vibration signature or sound signature change. Your smart speaker in your house, your Alexa, is using neural networks for a variety of purposes. So AI is around us. We call this edge AI. And the real problem that faces edge AI is actually the same one that's facing the cloud, and that is power. So we've probably, many of us have seen Sam Altman and a bunch of other people like him, leaders like him, talking about how energy is really critical for the data center, and it certainly is for the data center, right? I mean, we just can't deliver enough power to these data centers to power all the electronics, and in particular all the new AI chips. But the power needed in the data center is kind of a threat to how cheap those data centers are to operate. They're going to have AI. They're going to be able to do what they need to do. It's just there's going to be slightly less AI per dollar, or slightly more AI per dollar. At the edge, the power problem is actually existential. It's the difference between the product existing or the feature existing and it not existing. This power problem. AI requires so much energy, so much power that in many cases it's just not making the cut. It's not getting included in the products because they just can't make it work. And this is the problem that Ambiq exists to solve. I'll talk more about in a moment exactly how we do that and what our unique technology is. But it's this power need that motivates Ambiq's existence. Company was founded back in 2010, really to solve this problem. Yes, back in 2010, AI wasn't something that the common person was talking about, but we were starting to talk about the Internet of Things and putting electronics where it wasn't before. In fact, Ambiq's name, Ambiq, means ambient IQ, ambient intelligence. The idea is that we're embedding intelligence where there was none before. And so over the past few years, we've seen an evolution where adding intelligence to things means, neural networks. So company's about 200 people. We've got a really strong patent base and a technology base that I'll talk about in the next slide. And we ship more than 250 million units to all sorts of markets where intelligence is needed. And so if you look at our markets today, we're heavily into digital health. We're into consumer wearables, consumer hearables. We're in all sorts of smart home and smart building devices. We have customers in the industrial IoT space. And the one thing that's common between all of these markets, they're highly varied markets, but the thing that's common is that today they're starting to add neural networks. They're starting to have a hunger for intelligence that goes beyond what could be achieved without neural networks. And in the case of industrial IoT devices, it's what I said on the previous or 2 slides ago. It's that you've got machine health monitors looking at vibration signatures. In wearables and hearables, it's the heart health detection and the sleep detection that's happening. Digital health has all sorts of more interesting clinical analogs to that. So we're just seeing the start of what is possible when you bring AI to these devices, but it's an exciting time for sure. So I said earlier that power is the problem, right? If you want to bring all the compute that's needed to make AI possible, it's gonna strain tiny little batteries that you might find in one of these devices. And so you need a fundamentally different way of doing the chip design on the inside. So there's two options, right? One is strap a huge battery to this thing, so walk around with a car battery on my arm, or we take the chips down in power consumption, and that's what Ambiq specializes in. Our unique approach to that is called something we call SPOT, sub-threshold power optimized technology. It's based on a concept that was developed decades ago called sub-threshold or near threshold operation. And the basics are like this. Conventional chip design, we think in zeros and ones, right? And we signal a digital 0 with 0 volts. We signal a digital 1 with a much higher voltage, like 1.2 volts, 1 volt, 0.8 volts, whatever. You get a really strong 1, really weak 0. It's very easy to tell the difference between the two. In sub-threshold, or near threshold, we're dropping the voltage much lower. So instead of signaling between 0 and 1 volt, we're signaling between 0 and maybe half a volt or 0.4 volts. And the benefit there, it's a very simple concept, but the benefit is you get voltage squared reduction in energy. So energy is going way down. Of course, as you drop voltage, at some point, the underlying switch, the transistor that we use to build these circuits, it's not fully on. Okay, we like to think of them in the digital world as a transistor is either on or it's off. Well, in sub-threshold and near threshold, you're not really sure which one it is. You're kind of sitting in the middle. And to first order, that sounds simple, but it brings up 3 really fundamental challenges. One of those is that you have a near exponential sensitivity to manufacturing variations. So every transistor that comes off the manufacturing line is slightly different than the other. And that causes exponential changes in performance. Voltage changes. So I've got a battery voltage coming in, I've got on-chip noise. These things can cause exponential fluctuations in performance. And then similarly, as the ambient temperature changes, so as I go from the freezer, my walk-in freezer to the heat outside here in Texas, you get a dramatic change in performance because of that. These basically make it almost impossible to design in this regime, but that's where Ambiq has come in. We've developed this whole technology platform that we call SPOT, and it's a whole host of techniques. If you look in the upper right corner of this slide, it's a bunch of circuit techniques spanning digital, analog, memories. Also includes manufacturing test techniques. And when you add all those things up, it makes it a whole lot easier to operate in the near threshold and sub-threshold regions. And that's something that we've developed over more than a decade of operation, that we've protected with a great deal of patents. And the upshot of this is actually really simple. You can ignore all that technology stuff and really just focus on this. If you look at our chips compared to the competition, for similarly featured devices, we consume between 3 and 10 times less power than what's out there today. And that translates to, as we like to say, the end of AI battery anxiety. And so what do you do with that? Yes, you can run for a longer battery life, right? You can take a device that used to run for a day on a battery and make it last a week. But more compelling is when our customers do things like they replace a traditional algorithm with a neural network to improve accuracy. So we saw that happening, as I said, in wearables. Your heart health algorithms are getting replaced by neural networks, and magically they get better in terms of accuracy. You can also put bigger and better neural networks on device. So the thing that we figured out about neural networks is that they almost seem to be growing weekly in size, right? You go from last week, neural networks were this big. This week, they found a way to increase performance by making them somewhat bigger. Next week, they'll continue to grow. So you can increase accuracy, increase performance, increase capability by going to a bigger AI model without compromising battery life. And then you can also run them faster. So sometimes it's useful to have a network that's doing speech detection or speech recognition or whatever, and running it faster can improve performance as well, or increase my capability. So a lot of flexibility. I frankly don't care how my customer uses that flexibility. We've given it to them, and I think that's quite powerful. And so we, as Ambiq, bring this all together in the form of chips that we sell. So we're a chip vendor. We sell microprocessors today for edge use cases. And if you were to break open a typical chip, what we call our flagship family, Apollo, there's 5 different families of Apollo already out there with customers. But if you break those open, what you're gonna find is, first, you're gonna find a compute cluster that offers the lowest power general purpose CPU operation, but also great AI acceleration. And on the Apollo 3 and Apollo 4 generations, that's generally software-based AI. So you're running neural networks that run in the corner of the CPU using all the standard resources. With Apollo 5, the one that we just launched earlier this year, there's specialized vector acceleration that's even more efficient and more performant. And then we have next generation products that will have actual neural processing units, a whole separate microprocessor core that's dedicated to accelerating neural networks at very, very low power and very high performance. But that's not enough. Spot is great because you can apply it to that compute element. But there's so much other stuff that you do in these systems. Inference, the AI piece, is just a small slice of that, right? So imagine a typical system. You have to do sensing of the outside data. You've got microphones and heart rate sensors and motion sensors and all sorts of things. You got to bring that data on chip efficiently, and then you got to pre-process it. You got to run security operations, and you maybe have some UI. So you've got a display that you've got to talk to. So you've got to do all that stuff efficiently. Spot applies to all that stuff too. So there's a lot of really interesting, weird AI approaches that have come up today, but they often or usually neglect to focus on this stuff. So if you break open Apollo, you're also going to find a GPU for managing the display. You're going to find sensor interfaces, all implemented using Spot. And then finally, you also have to communicate off chip. So these are generally wireless devices. They're battery powered. They're remote. Having low power radio, all the digital interfaces to talk to other systems like USB, et cetera. These have to be present, and they have to be energy efficient. Again, something Ambiq is really, really good at. So what you're going to find with Apollo is the most well-rounded solutions out there. And I do want to mention this. While we are a chip company, we're a merchant chip company that sells silicon to our customers. It's a highly versatile technology. We've chosen to start with MCU products. We can build with that same technology applications processors, so much bigger processors capable of running Linux. We can build standalone AI accelerators. We can build sensors, radios. We can sell them into all sorts of markets, industrial, medical, even data center, right? That's not a market that we're frankly equipped to attack today, but the technology is well suited to that. And then we today, as I said, sell into certain verticals with these MCU products today as a standalone chip, but it is actually very possible for us to do an IP licensing model. It's not something that we're explicitly pursuing with great effort just yet, but it's something that we're preparing to do in the future. And I think what's important is that we're a low power technology company more than anything. We attack edge AI opportunities, but at the core, we're solving power problems that don't care about market, don't care about product type. And I think that's very powerful as we look toward the future. So just one brief comment on total solution before I wrap up here. Um, I said earlier that you got to address the power consumption problem for the full signal chain, from sensing to compute to radio, but it doesn't stop there. You also have to look above that. Our customers today, if I just give them an amazing piece of hardware, they can't do anything with it, right? You need the whole software stack up that sits above it. So when we give a product to a customer, it has the MCU, but it also has a whole bunch of software, and then it has a whole AI stack that sits on top of that. And so we have a product that we call Neural Spot. Neural Spot it covers a bunch of different product elements, but there's an SDK that helps get a customer going, writing neural networks. There's all sorts of tools that allow them to basically take their TensorFlow derived neural network and get it running on bare silicon down here, bare metal silicon down here. But what's also important is that we have a team internally that's building up what we call a model zoo of neural networks. These are pre-trained neural networks that have been developed for purposes like speech enhancement, for purposes like heart rate detection, or any number of other things. And we give these models, pre-trained models, to our customers. They can use them as examples to get going very quickly in developing their own neural networks. So again, it's important to provide not just the hardware, but the whole software stack that sits on top of that. So I'm going to end here and just say Edge AI is happening. We're seeing just the tip of the iceberg, just the beginnings of what's possible there. But it's going to be huge. It's in terms of end number, it's going to be far bigger than the data center. It's going to be billions upon billions, tens of billions of units that are running neural networks. And Ambiq uniquely solves the energy problem that's facing that coming wave of billions upon billions of devices. We've shipped 250 million units ourselves, and many of those today are running neural networks. And I want you to walk away with this feeling that Spot is a complete solution. Covers the compute, covers the sensing and UI, covers the communications, and it's one that is applicable to a broad range of markets. So with that said, Kevin, I'm happy to answer any questions.
Okay, great. Yeah, Scott, great overview. Yeah, I just want to go into details on a few points that you've made. First of all, you're an ARM-based CPU, and ARM has been known as the portable, or we'll say the low power processor, but it has been moving up and now is found in data centers. But with your sub-threshold technology, are you limited on what CPUs you can use, or can you use any architecture?
Yeah, good question. No, this is the beauty of Spot. I can apply it to any processor. So if you were to break open our chip today, what you would find is there's a ARM core, there is a GPU provided by another IP vendor. There's all sorts of third-party IP. There's all sorts of internally generated IP. All of it is running Spot, and that's the beauty of the approach. Is that our advantage lies at the kind of circuit level, or at the system level. And when a company like ARM gives me RTL, gives me software representation of their core, it doesn't matter to me what that is on the inside. And so that actually makes it easy as we look at integrating DSPs and neural processing units and Linux grade processors. We can bring all that IP in without too much of a challenge.
And you're just automatically, because you're working at 0.5 volts, that you're going to be lower power than someone else that has the exact same CPU.
Yeah, and you know what, I should also mention too, I mean, we talk a lot about operating at low voltage being the key thing is different, and of course it is, but the truth is that half of our energy advantage today is derived from that, but the other half is all kinds of other techniques that we're using. Actually, the best thing I can say about the engineers at Ambiq is that they're picojoule fanatics, right? They dream and think in energy units, and so that's led to a creation of a lot of unique technologies. Many of them patented, many of them trade secret. But yeah, definitely by virtue of operating at low voltage, we get kind of a magical benefit. But there's a lot of other stuff within the chip that gives us significant energy advantage as well.
Yeah, and maybe if I can just even get into a little more detailing, you showed a memory, so I imagine it's non-volatile memory, and also DRAM or maybe static RAM. Even to that level, do you do something that's different than industry standards for the memory?
Yes. So we have, if you were to again look at every Apollo chip, there is both non-volatile memory and SRAM, and The controllers for those are definitely taking advantage of Spot. The macros themselves have different levels of Spot use, so to speak. So, for example, in the case of SRAM, there are certain modes where we are indeed using Spot to operate at much lower voltages than is otherwise permitted. In both those cases, we are using off-the-shelf bit cells from TSMC. So TSMC is our manufacturing partner. They have great bit cells, and early on we looked at, should we go build our own memories, and the fact is, you shouldn't mess with the bit cell. Use the bit cell, but then everything else around it, really focus on hyper optimizing that. So I'm going to say that we have mixed use of Spot in and around the memories.
Okay, great. And you mentioned the software ecosystem, and maybe I'll even go back to the years when I was in sales and selling any type of processors, but microcontrollers. It gets to be a religion within a company, and to get them to change their legacy software, to change their design, very difficult. And can you talk about how do you go to market and get people to convert to your processor and your technology?
Yeah, and that's the beauty of working with a company like ARM, or even now RISC-V has a big enough following that you can convince customers to do this. But that's why we originally chose ARM. Is everybody knows how to write code for ARM cores? They have all the development tools. They might have a code base that's optimized for ARM SimSys libraries, which are a standard set of libraries that everybody supports. So just anecdotally, what I can say is we have customers. I'm thinking of one customer in particular who, in a matter of a couple of days, was able to port from a competitor solution to our solution. This was brand new product, port the operating system in maybe 2 days. So the similarity of our chip usage model to all of our competitors should be apparent very quickly. Of course, there are differences, but over time, we've done a good job in developing all the software libraries, all the software examples, such that porting can be pretty quick. But if you're used to writing your software using Kyle IDE from ARM and their ARM compiler, you can very quickly port. If you use the open source GCC and GDB environment, you can use that. More likely than not, whatever tool chain you're used to is something that you can port over very quickly with Apollo.
Okay, great. Yeah, and I guess that's the reason why there are other options out there like RISC-V you mentioned, but ARM is just bigger, and you can solve the problem with any CPU, right? Is that the
yeah, that's true. And what I will say is that the CPU is it's really important, right? No doubt the CPU is important. It's got to be usable. But the importance of the CPU in system is diminishing somewhat over time. So we have, we have multiple CPU cores in our latest chips. We've got a GPU core, as I mentioned. We've got all kinds of other accelerators and interfaces, and there will be DSPs and NPUs coming. So the impact of any one individual core is diminishing somewhat, which actually makes things interesting for a company like, or not a company, but for a movement like RISC-V, right? Where there are certainly processor cores where I could swap out one of the proprietary cores and put in a RISC-V core. So definitely interesting times for heterogeneous CPU architectures.
Yeah, and maybe just maybe I'll even bring it up my phone again, or my handset. When I show the display to people, especially outside, that's the first thing everyone notices is the bright OLED display. And that's part of your feature set that you're delivering.
Well, so we support, it's the thing that's been amazing to me over the last 7 or 8 years is how quickly these displays on mobile devices, whether it's a watch or it's a thermostat or any number of other things, the displays have moved forward very, very quickly. We're accustomed to using, our mobile phones, and we want everything that we work with to look and feel like that. And that has imposed requirements on us. So we've had to add GPU, as I said earlier. Big thing that comes along with that is a lot of memory. Putting big rich displays means you got to have a lot of memory. That of course comes with power challenges that we've had to solve along the way. So, things, even just the power of, if I've got a frame buffer for a display, the power of that thing sitting there in a memory is so astronomical that I've had to do some pretty special things to bring it down, just sitting there doing nothing. But there's, display controllers and all sorts of things. So yeah, we contribute a lot to that. A lot of that is just good display technology that's coming along, getting lower power. And I've got some excitement about some of the things like micro LED displays that are coming down the pike.
Great. And just one more question on the technology side, into going into the depth. You mentioned it in your presentation about the sub-threshold being trickier with process technology, because as good as TSMC might be, their transistors might vary a little bit. And do you have an issue that you can't go to multiple foundries? You have to qualify one foundry.
So the technology is very portable to different foundries, and that's evidenced by the fact that we worked with TSMC to go from 180 nanometers to 90 to 40 to 22, and now we're looking beyond 22, or we're working beyond 22. Porting to a different foundry would be straightforward. That said, TSMC has been an indispensable partner. They're the best foundry in the world, highest quality, and they have truly been there for us. So when we get a new chip back, they're right there to help us make sure that it gets going. They're there to help expedite chips through fab. So I think when you're pushing boundaries on a lot of different fronts, pushing transistors to operate where they don't want to go, you got to minimize the variables elsewhere, right? So let's ensure that quality is the highest possible, so that I'm not worried about that, and I can go worry about actually the truly difficult things that are unsolved problems. So TSMC has been there. We've developed a lot of methodology for porting from node to node, and so I'm not, at the moment, I'm not focused on porting to, say, different foundries. I'm more focused on how do I advance my process to the next node and the next node after that. Because there are new challenges that pop up, right? I mean, the funny thing is we've solved all the challenges we've faced, but the scale of our chips has gotten bigger with each generation. So as much as you start to think, oh, I'm really understanding all the challenges, the next node always brings a new wave of things to solve.
So I'd like to change topics a little more and start talking more about the AI and the end markets. We did host a data center tour about a month ago, and the CEO of the company explained, right away, he gave a presentation to 10 investors or so that we had, saying that we're out of power. So we got plenty of room in our building. We could put in more equipment, but we don't have any power to add the equipment. So how is edge AI going to help solve that problem? That all this work that's happening within the data center, can it get pushed out to the edge and save power?
Yeah. Yeah, and I can't. What I'm really not sure of is edge AI going to solve that problem, or is it just going to prevent the problem from getting worse? I mean, there's two options that we see with customers. Some customers have elected to say, "Oof, I don't have enough horsepower to do this processing here at the edge," or whatever the battery powered device is. And so they ship raw data up to the cloud and do the processing there. And the problem is that is not scalable, right? If you think about your average motion sensor in a building, or video camera, or even your fitness wearable, these things generate an astronomical amount of data, right? I mean, the number of sensors on this thing collecting data hundreds or thousands of times per second really adds up quickly. And so what we find is that's not a scalable model to send things up to the cloud. Much easier to stay here at the edge and do the computation here. So I don't think the edge AI explosion is big enough yet that the power problems you just alluded to, the data center problems are strained too much by the edge use case. But they will be. It's going to get 10 times or 100 times worse if we don't do something about it. So back to my original statement, I think edge AI will prevent this problem from exploding by another order of magnitude or two. Probably there are, certainly when we look at customers, there's a handful of applications and use cases where they can migrate stuff that's in the cloud out to the edge, and that's up to us to give a good solution that makes that feasible. But I think it's more preventing the wave of edge devices from absolutely imploding the data centers. And I guess what I'll say is we have some people here at the company that participated in the whole mobile explosion right before this. So if the big wave of electronics before AI and edge AI was mobile phones. What was interesting was that mobile phones and data center went hand in hand. So as mobile phone traffic went up, data center traffic went up as well, right? I mean, I'm every time I open this thing, it's routing requests through various data centers based on what service I'm using. I think we'll see the same thing here. I think both will go hand in hand. I think that there will be as Edge AI grows, data centers will grow. But I think I feel a sense of responsibility at my company that we have to make sure that AI is possible here, so that we don't, cause these data centers to implode on themselves.
And you mentioned your model zoo, which is very interesting to me for a company on the edge. It's, I guess NVIDIA shows a presentation all the time of how big these models are getting, and how much memory it's going to take to run them. And but you're able to, how do you take these large language models, or even say other models that have trillions of parameters, and break it down so that your processor can operate on it?
Yeah, I mean, first of all, the models we're talking about are much simpler than these big cloud-based large language models. So we are there's a whole host of models that we offer, from a few tens of kilobytes to things that are closer to megabytes. But the biggest models we're talking about are a few megabytes, and the next generation of chips that we have will support tens of megabytes of model sizes. So, the real question is, how do you cram something really usable into a 10 megabyte or 20 megabyte or 30 megabyte footprint? And there's a lot of tools for doing that. Part of it is right sizing the problem. So, as much as we've seen really crazy proposals on radical new accelerator architectures, et cetera, the most effective thing you can do is actually just design your network a bit intelligently. So maybe just a dumb example. If I were to try and port a large language model from the cloud to the edge, I don't need a ChatGPT caliber large language model. I need one tailored to my use case. So if my use case is, again, since this just happens to be the device right in front of me, if I want to be able to talk to my watch, let's say, and instead of click buttons, this is complex, I want to just talk to it naturally. There's only 50 or 100 things that my watch can conceivably do. So you need a model, in this case, maybe a large language model, or maybe it's some other type of model, capable of understanding those 50 to 100 intents that you could have, right? You don't need it to write you a poem, right? You don't need to write a song about, my day of work at Ambiq. I needed to be able to start a run. I need to be able to, have it take a note. I need to be able to create a calendar invite, whatever. That's a much simpler problem. The model can be commensurately smaller, and that all works. And then there's a whole bunch of other stuff that we can do. So I'm not going to get into the technical details, but there's things called, there's a concept called pruning, where we can prune away weights that don't really matter. You can compress these things. There's all sorts of compression methodologies that can get these models to be smaller. And then there's also what I'll say is that the solution is not to be 100% edge based. The solution is to do as much as you can at the edge, and then graduate to maybe the phone, or to a gateway, or to the cloud when you need to. And so you have a front end that's in the case of imagine I want to put a Alexa in every device around me. I put a front end that's first detecting voice, and then I figure out, does it say Alexa? And if it says Alexa, then I have a network that can maybe construct the sentence that was uttered, and then I send it to the cloud for actual analysis. So there's a series of neural networks that's needed to do everything I just described, but those are relatively modest neural networks. Do the heavy lifting in the cloud, or on a phone, or a tablet, or whatever, and do the rest locally. So I think there's a lot of approaches to managing that. Again, back to your original question, in our model zoo, these are relatively simple models. Something that's doing heart rate detection, for example, and looking at heart rate variability. These are models that are on the order of tens of kilobytes, right? They're not trillions of parameters, and that sounds really small, but in fact, it's somewhat large compared to the algorithm that was the traditional filter and algorithm that was used to implement that. It might be 3 or 4 times larger, but the performance that you get out of that is priceless.
Okay. I'll open it up for questions from the audience. If anybody, I think you just type it in, and I'll ask the question. But I'll go into also, when I'm thinking about all these devices, and your market is billions of units are available for you, that and growing. But what about security? We all know about viruses, and if you're getting billions of devices that are out there on the edge and gathering data, how do you build in security into your processors?
Yeah, security, and this really happened before the AI explosion for us. Security, as we've put devices all around us, as we've embedded chips in our, on our homes and on our bodies and all sorts of places, security has come to the forefront. And that's definitely, as I described the AI vision of what's possible, it can go one of two ways. People can get excited about it, or they can get really nervous about the security implications. And so that puts the burden on us, and it's a hardware and software problem. We have all the security features you could imagine. We've been put through the ringer by some of the biggest consumer brands out there. And we have things like a secure boot process, a secure boot flow. So every time that chip boots up, it's done so securely. It ensures that the firmware image that's running on it is authentic. If you do over-the-air updates where you're providing new software, it has a process by which it assesses the security level there and makes good decisions. For our customers' sake, our customers have assets that they want to protect, right? So they want to know that one of their competitors can't hack in and extract their software secrets just by buying one of these devices. And so we have capabilities, so-called secure lifecycle management, where we can lock down elements of our chips so that our customers' secrets are safe, and by extension, their customers' secrets are safe. And then there's a whole software stack that sits on top of it. So you need the basic hardware building blocks, things like random number generators and cryptographic accelerators, but then you need the whole software stack that sits on top of it. So are all edge AI security loopholes closed? Absolutely not. No way. And I think that we're, broadly speaking, the industry is vulnerable to all sorts of hacks. But I will say that from our perspective, we take security very seriously. It's probably one of the top 3 most important things that we do. If power and performance are big ones, security is the other, third leg on that stool. So security is indeed very important. It's something that we take seriously and will continue to evolve. If you look at our Apollo 3 generation, security was a large, mostly software based approach. With Apollo 4 and Apollo 5, heavily hardware enabled. And with future generations, I think you'll continue to see us expand upon security accommodations.
Okay, great. And maybe when we talk about this size of this market, and there's some of the obvious companies out there like Fitbit, but what is your go-to-market? How do you find new customers? How does you get the word around about this sub-threshold? And maybe I even want to ask about competitors. Is there anyone else that has sub-threshold technology?
Yeah, so I'll start with the latter part first, and then get to the former. So other competitors. I mean, I would say that the biggest competition that we face is the competition of good enough. It's customer who is used to dealing with vendor A, vendor B, vendor C. They've been using them for 20 years. They buy product from them. And so that's an easy, comfortable solution. And the competitors are generally relying on TSMC to do the heavy lifting of Moore's Law and moving power consumption forward, moving performance forward. So we feel that we can manage that. As far as our go-to-market strategy, we serve a lot of different markets. So the challenge is, yes, we serve consumer markets. There, it's relatively straightforward. In any given vertical, there's 4 or 5 customers who dominate the volume, and you can go to them and we do direct support. We have a big FAE team that supports them, big software team that supports them. But as we have branched into new areas like healthcare and smart home and smart industrial, the customer base is a lot more scattered, and so we have a sales rep and distribution network, depending on where you are in the world, that we use to access those customers. So we still have big alpha and beta customers that we'll go engage with directly there. But we also have a network of reps and disties that help us access a lot of those other markets. And what I'll say about that is you have to have a scalable support infrastructure to make all that work. So 5 years ago or 8 years ago, we weren't really ready to go engage those customers. We had a relatively small set of customers. We had a software team that was amazing, but could only support a handful of customers at a time. Over time, they built up software infrastructure, knowledge base with white papers and all sorts of FAQs and this sort of thing. The model zoo that I talked about earlier, Neural Spot, all of these things add up to a platform, a software platform that's a lot more usable, which means that we're ready to go and engage that the sales force, the channel, to go talk to hundreds of customers that might buy only 10,000 or 100,000 units a year. So we're in the process of expanding to all sorts of new markets. It's really interesting. It makes my days a lot more interesting. And so what I think you'll see is all these little icons on the slide here. You're going to see Ambiq inside of all these different types of use cases. Yes, our volume today is a lot of consumer electronics products, but if you look at all the new design-in activity, there's a lot of stuff that falls well outside of that, and that's exciting. I think it's exciting for the edge AI explosion too, right? I mean, part of it was that a lot of the innovation was happening in these consumer products. They're the quickest to adopt the new technologies, and what we're now seeing is a lot of these other markets are following behind, and that's making Ambiq's technology quite a hot commodity.
Yeah, and it seems like that's what you're doing is this strategy that's worked, I guess, for technology throughout the years. x86 was considered a toy when it was in a PC, and now it's running the servers and data centers and replaced mainframes. And the ARM is now moving up, and you've solved a power problem, and I would think that's harder to do than performance. And now you're going to take your product and move to higher performances. If you can tell me a little more about that roadmap of what you're planning to do.
Yeah, so we have driven up performance dramatically just over the last 10 years. So if you look at the original Apollo generation, it ran at 24 megahertz. The newest one runs more than 10 times faster at peak. And yet the energy efficiency is about 8 times better. So it's 8 times more efficient, 10 times faster. That's a pretty amazing inversion that we've done. Moving forward, we will continue to drive performance up. Some of that is through innovations that we're going to be deploying. Some of it is through help from our foundry partner from TSMC, right? Moore's Law is alive and well. We're in 22 nanometers and 40 nanometers for most of our volume today. And so we have a long way to go to keep scaling and to keep driving up performance. So that helps. And then the other thing that helps us is that these workloads, as I said earlier, are shifting more and more towards neural networks. Neural networks are highly parallelized workloads. And so I can achieve high performance. This is not about the late 90s, early 2000s gigahertz wars where we're just cranking up clock rates to make chips go faster. Now it's about getting more intelligent and putting execution units in parallel. So neural networks really map well to parallel operations. That's why NVIDIA is where they are today, because they happen to have a really good parallel math engine. What that means for us is I can really achieve crazy high performance numbers by going parallel. So if you look at next generation products, what you're going to see is, yes, they get faster. Raw clock frequencies will be faster, partially due to architectural enhancements that we've made, partially due to help from TSMC on the Moore's Law front, and then partially because of new enhancements we've made in support of neural networks where we're adding explicit parallel accelerators. When you add all that up, it's going to be wild what kind of performances we hit, and at crazy low energy consumption. I mean, I'm really excited about where the world's going. And part of it is that every week I'm overwhelmed. I said this earlier, I think, but I'm overwhelmed by the pace of improvement in neural networks. Every week it seems like there's new announcements, there's new developments. They're getting bigger, they're getting more memory hungry, more power hungry. And so we have to do this, but listen, we're meeting with customers every day that are telling us pretty astounding things about what their plans are for edge AI, and I'm really excited. I wish we could just flash forward to 3 or 5 years from now, because there's going to be some pretty wild advancements.
That's great. Just one question from the audience. It's your competition against Qualcomm. Do you consider them a competitor? How do you compete against Qualcomm?
Yeah, I mean, they're like any chip company. They're a partner and a competitor, right? I mean, there are designs that we're in today where Qualcomm is sitting next to us. They serve a different role in the market, right? I mean, they're a cell phone chip company that is bringing that same architecture to other spaces. They're bringing it to the data center. They're bringing it to edge devices, that means that their technology is really high performance, really good for peak performance use cases, really good at running Android and Linux and these high level operating systems. Not as good when your objective is to consume as little energy as possible and build a more stripped down experience. We're coming from the bottom up and meeting them in the middle, and so I think that means that they end up being pretty complementary. But indeed, yeah, any chip company that's not us is a competitor to us, right? It doesn't matter how complementary it is on the whole. So I just think very different approach to things. I think their solution is just kind of complete. It's a very, very complete solution. It has every wireless standard known to man and super, super high performance. But when low power is needed, you're going to find us standing next to them.
Okay, with that, Scott, thank you very much. It was a great presentation. Very excited for your company.
Appreciate it. Thanks for having me.
Yeah, thanks.